Hello students, in the last session we have seen the basic elements of a mechanical translational system and mechanical rotational system, that is the mass, damper and the spring. In case of mechanical rotational system it is the moment of inertia, damper and spring, and we have seen even the steps of finding a transfer function for a mechanical translational system. So in this session we will be looking into two examples, that is one for mechanical translation system and another for mechanical rotational system, so that you will have a better understanding how to derive the transfer function of mechanical systems. Let's get into the session. So here is an example for mechanical translational system. So the problem is to find the transfer function of the system. Before we start, let us have an analysis of the given system. Here you can see that there are two mass points, that is M1 and M2. There is a friction between this mass and this ground. This slashed line is ground. The frictional component between this mass and the ground is given by B1, and the frictional component between mass 2 and the ground is given by B2. There is a elasticity component connected between ground and the mass 1, K1, that is K1, and there is K connected between M1 and M2, also B connected between M1 and M2. So first point that we have to do is identify the nodes. So I told you that masses usually acts as nodes. So you can see here this particular mass M1 will act as one node, because here we have connected other elements like B1, K1, B, K. So there are how many elements? 5 elements. 1, 2, 3, 4 and 5. That is K1, M1, B1, K and B. So there is another node here M2, for which you have 4 elements connected, that is B, K, M2 and B2. The displacement of this node is taken as X, and the displacement of this node 1 is taken as X1. So now we will start to write the force balance equation for node 1 and node 2. You can see that there is a force applied only in the second node. So there is no force acting on the first node. So the force balance equation will be like the opposing forces due to M1, B1, K1, B and K. Sum of all these things will be equal to 0, because there is no input force acting on it. So this input force is 0, and all the opposing forces are written in the left hand side. So this is your node 1 expression. Similarly, you have got to write a node 2 expression also. So the opposing force due to M2, B2, K, B, summing all these things should be equal to F of t. That will be the node 2 equation. Now let's write the differential equation for the node 1. So there are 5 elements connected, 1, M1, B1, K, B and K1. The opposing force due to M1 is M1 into d square x1 by dt square, because the displacement corresponding to node 1 is x1. So the expression is Fm1 is equal to capital M1 into d square x1 by dt square. The opposing force due to this damper B1 is equal to B1 into dx1 by dt. The opposing force due to this spring K1 is K1 into x1. But now for these two elements B and K, they are connected between x1, and that is the displacement x1, and displacement x, that is they are connected between the node 1 and node 2. So the net displacement will be x1 minus x. So when you write it for B, it is B into d by dt of x1 minus x. For K also, it is K into x1 minus x is equal to 0. That will be the differential equation for node 1. So you can see that in the next slide, the equation. So this is the equation. You can see that whatever we were telling, that is written here, that is m1 into d square x1 by dt square plus b1 into dx1 by dt plus b into d by dt x1 minus x, because this element was connected between the two nodes, and here also k was connected between the two nodes x1 and that is the displacement of node 1 is x1 and the displacement of node 2 is x. So it is written like this, whereas k1 was purely connected only to node 1, so it is written as k1 into x1. There is no input force, so it is equal to 0. So this is the differential equation. Now take the Laplace transformation on it. After taking Laplace transformation, it becomes s square into x1 of s. This small x1 becomes capital X1. This m1 is a constant. On taking Laplace transformation of d square by dt square of x1, it is s square into capital X1 of s. Similarly for this, it is a dx1 by dt, so it is s into capital X1 of s. Small letter x1 becomes capital letter here in the Laplace domain. Here also b is a constant, so this has to be replaced by s into capital X1 of s minus s into capital X of s. Taking s common, you get this expression. This is a k1 into capital X1 of s. After taking Laplace on this, you will get it as k into capital X1 of s minus x of s is equal to 0. So just to do a small rearrangement here, so that you get expression for capital X1 of s. So now we will write the expression for node 2. So we were talking like 4 elements were acting on the node 2, and there was an input force f of t. M2, B, K and B2 were the 4 elements. Among these 4 elements, this B and K were between the node 1 and node 2. So when you write the expression for Fm2, it is the mass m2 into d square x by dt. This is the displacement of node 2 plus b into d by dt of x minus x1, that is the displacement of node 2 minus displacement of node 1, because we are writing the equation for node 2. It is always with respect to node 2 now, so the displacement becomes x minus x1. This is a key point that you have to note. When we wrote it for node 1, this FB was d by dt of x1 minus x. Now it will be d by dt of x minus x1. That is node 2's displacement minus node 1's displacement. Similar is the case with the k. K was also connected between node 1 and 2, because we are writing the node equation for the second node. So it is k into displacement of second node minus displacement of first node. So x minus x1. Here also it is, this is what B2 was purely related to node 2. So it is B2 into dx by dt, that is displacement of node 2, is equal to f of t. So just take Laplace transformation on it. Similarly, you will get these are all constants m2, b, k, b2. So you have to take Laplace on this. So you get s square into capital X of s. Similar is the case here. X of s minus x1 of s, x of s minus x1 of s, s into x of s. For this particular element, it is s into x of s is equal to f of t. On taking Laplace transformation becomes capital F of s. So now a small rearrangement is made where we have taken x of s element separately and x1 of s element separately, so that it's easy for us now to apply the equation 1 here. So equation 1, we had the expression for x1 of s. Substituting that x1 of s in the second equation, x1 of s vanishes. So you get everything in terms of x of s and f of s. Here we have just done a substitution of equation 1 in 2. That's it, nothing more than that. So now you have only two variables, that is f of s and x of s. Just do some rearrangement. rearrangement so that you get x of s by f of s. So this is the transfer function of the system. You can take some time so that you do it in your notebook, this particular reduction. We have done nothing, like we have just taken x of s common and x of s by f of s. That is, this is the output of the node 2. Here the output was taken as the displacement of second node. So the output variable is x of s and the input is your f of t. In Laplace domain it is f of s. So output by input gives you the transfer function. Here there is another example, but this is a rotational system. Mostly all the procedures are same, except that instead of mass you will have here J, that is moment of inertia. Instead of linear force you will have a rotational force, that is the torque here. So that is the major difference. Other things are very much similar to what we have done earlier. So this is a system. You can see that there are two nodes, one at J1 and another one at J2. To J1 there are two elements connected. One is J1 itself and another one is K. For J2 there are three elements, that is K, J2 and a damper B. So there are three elements connected. So the torque T is applied to node 1. There is no torque applied to node 2. So now we have got to write the torque balance equation here. So the opposing forces due to this J1 and K, sum of these two is equal to applied torque. So Tj1 plus Tk is equal to T. That is the node 1 equation. So obviously node 2 equation will be Tj2 plus Tk plus Tb is equal to 0. There is no applied torque. So all the opposing forces due to J2, K and B will be equal to 0. That will be the node 2 equation. So now let us write the differential equation at node 1. So here the displacement, that is angular displacement for node 1 is not given. So let us assume it as theta 1. Whereas for the node 2 the angular displacement given is theta. Let us have it here for node 1 as, if the variable is not given you can assume a variable. So let us take it as theta 1. So the theta 1 will be the displacement, that is angular displacement for node 1. So you just write the torque equations here. So it is J1 into d square theta 1 by dt square plus K was connected between node 1 and node 2. So the displacement is theta 1 minus theta is equal to applied torque T. So when you take Laplace transformation, it becomes J1 and K are constants. So J1 will be as such J1. So when you take Laplace on this, it is S square into theta 1 of S. Okay. So when you take Laplace on this, it becomes K into theta 1 of S minus theta of S. So I have taken theta 1 of S component separately and theta of S component separately is equal to T of S. So node 2, you know that three components were connected. Tj2 plus Tb plus Tk is equal to 0. There was no applied torque there. Write the differential equation. It is J2 into d square theta by dt square plus B into d theta by dt. K was connected between node 2 and node 1. So the displacement here now you should write it as theta minus theta 1. That is the displacement at node 2 minus the displacement at node 1 is equal to 0. Just take Laplace on this. You get this expression. So this expression you can see that there is theta of S and theta 1 of S. Find the theta 1 of S in terms of theta of S. So substitute this theta 1 of s in the first equation, so that you get the theta 1 of s eliminated, and there is only two variables, that is theta of s and t of s. It's very simple. Find from the second equation theta 1 of s and substitute that theta 1 of s here. So once you replace this theta 1 of s by this expression, you get the theta 1 of s eliminated. You have only two variables, t of s and theta of s. So just rearrange it, reduce it, so that you get it as theta 1 of s by t of s. So this is your transfer function expression. So students have to take some time and derive this, or take some time to reduce it to get your transfer function here.